So in the previous two videos, we looked at some applications of the ideal gas law, mainly how to use that equation in calculating a gas's molar mass and calculating the density of a gas. A third way we can use a form of the ideal gas law is when calculating a substance's osmotic pressure, which for reasons that are unknown to me, scientists use the pi Greek letter to designate osmotic pressure. That doesn't mean 3.14. This is just the variable or the symbol that is used to designate osmotic pressure. So osmosis is a term you probably have been familiar with from a biology or physical science class. Osmosis is essentially the flow of solvent, liquid molecules, from a less concentrated area to a more concentrated area. And that flow of solvent occurs through a semi-permeable membrane. So osmosis happens all the time in our body, in our cells. For example, we've got a red blood cell here on the left. In this scenario, the movement of osmosis is equal to the movement out of the cell. So the osmosis movement in that situation is equal. If you have a red blood cell, in this case, in a solution that is really dilute or hypotonic, you're going to have a situation where you've got an increase of osmosis of water into your cell, and that could potentially damage or burst a red blood cell. Similarly, you could have a situation, another bad situation, where if you have a red blood cell that's in a very concentrated solution, where the movement of osmosis is such that it's going to shrink the red blood cell. So obviously, we want the cells in our body to not explode and not shrink. We want them to maintain their normal shape. So that's why osmotic pressure is really important to maintain with the biological fluids of an organism. And so the pressure that is required to stop the osmotic flow or to equal the osmotic flow of a cell is called osmotic pressure. It is related to the amount of particles in the solute. It is incredibly important for nurses when preparing IV solutions, since it's related to the concentration of solute particles. You need to make sure that the concentration of your solution is going to provide an osmotic pressure that gives you an isotonic situation. For purposes in this chapter and for doing problems in this chapter, you can calculate osmotic pressure by using a form of the ideal gas law, which is this equation up here. So osmotic pressure is equal to IMRT, where I is equal to 1. It's related to the amount of solute that's present. If you go on in chemistry, you'll talk more about this I factor, but for these problems in this class, I will give you what I is. You will assume it to be 1 unless I tell you otherwise. So think about that. I is a constant for a particular molecule. M is the molarity of your IV solution. R is the gas constant in our favorite units of liter atmosphere mole Kelvin. And T is the temperature in Kelvin. Okay? So obviously you will have your notes when doing practice problems and exams, so you will have this equation ready to use when need be. So let's say we're doing a problem like this. We're given the average osmotic pressure of blood as 7.7 atmospheres at 25 degrees Celsius. What molarity of glucose will be isotonic or equals to or corresponds to the osmotic pressure of blood? So since we're dealing with osmotic pressure and we're looking for molarity, we can use this equation, this form of the ideal gas law, to solve for molarity. So I've got that equation right here. We have the osmotic pressure as 7.7 atmospheres. We were given a temperature in Celsius, but we need to convert it to Kelvin. For all molecules that we will deal with in this course, the I will be equal to 1 unless I tell you in the problem otherwise. So for this problem, I is equal to 1. R is the gas constant. We need to solve for the molarity, M. And so hopefully you can see that to solve this equation for molarity, I'm going to divide both sides by IRT. And so doing that will give you M by itself, and so more neatly written will give you the equation that you need to solve for in this form. Plugging in the appropriate values in atmospheres, Kelvin, and the gas constant. You see your atmosphere units cancel, your Kelvin units cancel, and you're left with liters per mole in the denominator. When you flip that to the numerator, you get the units of moles per liter. And hopefully you remember from the previous chapter that the unit of mole per liter, that is the unit for molarity. So putting this in your calculator, you should get a concentration, a final answer of 0.31 molarity. That is the concentration of glucose that would be isotonic or corresponds to the osmotic pressure of blood. So I would encourage you, if you're a nurse or if you work in the ER and you've got some spare time, haha, but if you've got some spare time, take a look at an IV solution of glucose. And I think a lot of IV solutions list concentrations in terms of mass percent. But if they have it listed in terms of molarity, see how close the molarity is of that glucose IV to what we've calculated. So that is the third and final practical application that we will talk about using the ideal gas law, which is involving osmotic pressure.